All right, so let's take a look at the trig form of a complex number. So we talked about complex numbers, and remember, they are numbers that include I, the imaginary number. And so when we have a complex number, let's say z equals a plus bi, then we can graph that on the coordinate plane where the y-axis or the vertical axis is the imaginary and the x-axis is the real. That horizontal is the real. So we can graph it as the point AB, where A is that real number, and then B is the imaginary. All right, and we're just graphing it without the I in there. Okay, so if we take a look at the first example, we can plot z equals -6 minus 8i as -6, -8. So all we're doing is going to the left -6 and down 8. And so that is -6, -8, or -6 minus 8i. That would be how we graph it. Now we want to find its absolute value. And if we look just above, we know that the absolute value of -6 minus 8i is equal to the square of -6, I'm sorry, the square root of -6 squared plus -8 squared. And so -6 squared is 36, -8 quantity squared is 64. Add those together, you get 100. So the absolute value is 10. All right, let's take a look at the next page. So we have the trig form of the complex number. So this is just another way of writing the same number. So we have r times the cosine of theta plus I sine theta, where a is r times the cosine and b is r times the sine. If you take a look at r, notice that that was the same thing as the absolute value of the complex number. All right, and then the r is called the modulus, and the theta is called the argument. Okay, so for example number 2, we want to write the complex number z equals -7i in trig form. And so the first thing that I'm going to do, I like visuals, you know that, so I'm going to graph it. And so notice that there is no real number, so that's 0, right? So we're on that vertical axis, and we just go down to 7. So it's 0, -7, or -7i. Okay, so that's how we're going to graph that. All right. So then our r squared, or I'm sorry, our r, remember, is the square root of the real number, or the real number squared, plus that imaginary number squared. Okay, so that's the square root of 49, which is 7. So r is 7. And then we also want to look at what is this angle here, and that's 270 degrees, or 3 pi over 2. You might see it written different ways. So I'm just going to write it in degrees, but again, you might see it in radians. So it's r, which is 7, times the cosine of the angle, which was 270 degrees, plus I times the sine of the angle, which was 270 degrees. And that is it. All right, let's take a look at example number 3. Write the complex number z equals -2 minus 2 square root of 3i in trig form. Again, I like pictures, so I'm going to draw the picture. Notice that this would be like -2, -2 square root of 3. Since both of my variables, or both my parts of my ordered pair are negative, we're going to be in the third quadrant. Okay, so I have -2 and -2 square root of 3. Okay, so if we were to draw that triangle, remember that the vertical gets dropped to make that right angle with the x-axis. So that means that this side length is -2 square root of 3, and this side length is -2. Okay, And so really, that's the same thing as saying -1 and negative square root of 3, right? And so if we look at which angle is going to have negative square root of 3 and -1, well, remember on our unit circle, we have those values just over 2. Right? And so that might help you in looking at, okay, what is that angle going to be? You could also, plug it into the calculator and figure it out that way. Like maybe doing inverse cosine of -1/2. And that'll give it to you. So we want to, let's see, did I do that? Yeah, okay. So we know that that angle is going to be, well, the reference angle here, if you remember, is going to be 60 degrees. And so 60 degrees plus the 180 degrees is equal to 240. So we know that that angle is 240 degrees. So that's theta. And then remember that r is the square root of your -2 squared plus your -2 square root of 3 squared. And so then we get 4 plus 2 squared times 3, so that's going to be 12. So that's the square root of 16, so that equals 4. And then you're just plugging it in. So z equals r, which was 4, times the cosine of 240 degrees, which again, if you want to put that into terms of pi, that's going to be 4 pi over 3. Okay, so you might want to just make sure that you can go back and forth between radians and degrees, because you never know if the problem is going to be in radians or degrees. Okay, let's take a look at number 4. Write the complex number z equals 5 times the cosine of 7 pi over 6 plus I times 7 pi over 6. And notice these angles are always going to be the same. If they're not the same, something's not right. Go back and check. Maybe it's a typo, but if you have the complex number written that way, those numbers, those angle measures should be the same. So we're going to write that in standard form a plus bi. So again, I like pictures. So I'm going to draw that angle, and I know that it's in the third quadrant, right? And so, okay, so I know that this is 7 pi over 6, which is the same thing as 210 degrees. So I know my x value is the square root of 3 over 2, but it's negative since we're in that third quadrant. And then I have -1/2, remembering from my unit circle there. And all right, so then I am just going to replace those. So z equals 5 times negative square root of 3 over 2, and then plus I times -1/2. All right, and then we're going to distribute that 5. So -5 square root of 3 over 2 plus -5 halves times I. And if you want to rewrite that, you can. I would accept this as the answer, but if you want to rewrite it so that it's minus, if you don't like the plus minus thing, you can rewrite it like this. So either one of these two are acceptable answers, in my opinion. All right, let's take a look at the product and quotient of two complex numbers. All right, and so we have these formulas, and these two formulas, if it's on the test, you will be given those formulas. You don't have to memorize those. So we are going to look at first the product, and so that one is going to be this formula where we're multiplying z sub 1 and z sub 2. And they're fairly straightforward. You're basically just multiplying your r's, so 7 times 3, and then you're taking the angle measures and you're adding them together. So 3 pi over 2 plus pi over 2 is 4 pi over 2, which is really 2 pi, right? And then plus I times the sine of 2 pi, because remember, once you do it once, it's the same thing. And so that's going to be 21 times 1 plus I times 0, So really that's just 21. Okay, for the next problem, we are going to find the product again. And so we're going to use that same formula. Again, you're multiplying your r's. So that's 10 times 6 times the cosine of the sum of the two. So that would be 18 pi over 12, which we'll simplify in a minute, plus I sine of 18 pi over 12. Okay, and so we know that's 60. And then the cosine of 18 pi over 12, you can divide both of those by 6. So that ends up giving you 3 pi over 2. And that one is pretty easy to find because it's right there on the unit circle for us. And so the cosine of 3 pi over 2 is 0. And then the sine of 3 pi over 2 is -1. Because remember, that's 270 degrees. And then we multiply the 60. 60 times 0 is just 0. So we have -60i. And so that would be the product of those two complex numbers. All right, let's take a look at a division problem. And that's where we're going to use the second of the formulas. So this time we're dividing the r's and subtracting the angle measures. And this time order does matter. So we need to make sure that we are subtracting the z sub 1 angle minus the z sub 2 angle, because the z sub 1 was the numerator. Okay, so that's going to be 12 over 3 times the cosine of 70 minus 25, so that's 45 degrees, plus I times the sine of 45 degrees. Okay, and now it's just a matter of simplifying. So 12 divided by 3 is 4. The cosine of 45 degrees is square root of 2 over 2, plus I times, again, square root of 2 over 2. So when you multiply the 4, you end up getting 2 square root of 2 plus 2 square root of 2 times I. All right, let's take a look at this theorem. And, oh, went the wrong way. Meant to scroll down. So we have this theorem. I'm not very good at pronouncing this. I believe it's a French name, de Moore. I don't know. Anyway, so we want to use it to find 1 plus I to the 6th power. We could multiply that out, and it would take a while. And there's lots of room for error there. So an easier way to do this would be to just use this theorem. Okay? And so in order to do that, we first need to figure out what R is. So remember that R is the square root of your real number squared plus your imaginary number squared. And so that's just the square root of 2. And we know that the tangent, right, is going to be 1 over 1. Right? And so we know that the tangent is 1. And so the inverse tangent of 1 is equal to our angle. So that means our angle is 45 degrees. Oh, that should have been a theta. So we know our angle is 45 degrees. Okay. And so we now know what our sine and cosine are because it's 45 degrees. So z to the 6th is equal to the square root of 2 to the 6th power, that's our r to the n, times the cosine of 45 degrees. Oh wait, hold on. Not 45, we need to multiply the n. So the cosine of 6 times 45 degrees plus I times the sine of 6 times 45 degrees. Okay, and that multiplication of the 6 is important because it will help us know what quadrant we're in. All right, so the square root of 2 to the 6th power gives us 8, and this ends up being cosine of 270 degrees plus I sine of 270 degrees. And so we've got 8 times cosine of 270, which is 0, plus I times the sine of 270, which is negative 1. I don't know what I'm writing. Times negative 1. There we go. And then we distribute the 8. 8 times 0 is 0. 8 times negative 1i is negative 8i. And so that is a whole lot easier than trying to expand 1 plus I 6 times. All right, let's take a look at the last problem. We know that n is going to be 3 because it's the cube root. Our r is going to be 1 because it's really like 1 plus 0i, so the square root of 1 squared is just 1. So that's where that comes from. And so we can also find theta. If we think about this as being 1, 0, remember because there's no imaginary number there, then we know that theta is 0 degrees. So that kind of makes that easy, or 0 radians, depending on how you want to look at it. So our formula is z sub k is equal to the cube root of 1, because that's the nth root, times the cosine of, and we'll go with 0 plus, we'll do this in radians, so 0 degrees, I'm sorry, radians, plus 2 pi k all over 3, because remember, our n is 3 here, plus I times the sine of the same thing. Well, actually, that shouldn't be 0. That should be theta. Theta plus 2 pi k over 3. And really, theta is 0, so that's going to make this problem a whole lot easier. All right, so we'll simplify that a little bit. This cube root of 3 is just 1. So this is going to be the cosine of 2 pi k over 3, because remember, adding 0 to it doesn't really change it. And then plus I sine of 2 pi k over 3. And I suppose I could put parentheses around that. All right, so now we're going to find z sub 0, z sub 1, and z sub 2. Okay, so z sub 0, we're plugging in 0 for k. So cosine 2 pi times 0 is just going to be 0. So cosine of 0 plus I sine of 0, not theta, 0. And remember, cosine of 0 is 1. Sine of 0 is 0. So the answer is just 1 because I times 0 is 0. Then we have cosine of 2 pi times 1 over 3. So that's 2 pi over 3 plus I times sine of 2 pi over 3. And if you think back to your unit circle, the cosine of 2 pi over 3 is negative 1/2. And the sine of 2 pi over 3 is the square root of 3 over 2. So there's another root. And then the last root is the cosine of 2 pi times 2, so that's 4 pi over 3, plus I times sine of 4 pi over 3. And again, looking back to your unit circle, the cosine of 4 pi over 3 is negative 1/2, and the sine of 4 pi over 3 is negative 3, square root of 3, I'm sorry, over 2, and then don't forget your I with that. So these are the 3 roots of 1, the cube roots of 1.